So complexity, when we speak of the economy, we speak about complex systems. And even though we try to model these systems and, some PhDs and even some Nobel Prizes have been awarded with overly simplistic assumptions about how things work, when that's not really how things work. And anyone who's been involved in the economy or the markets can understand that we have, creation, new businesses, new opportunities, cooperation, self-organizing entities, self-organizing markets, and then competition, right? To then find the best products, services, create new products and services. And that's how the economy works. There's been an attempt to model this, and a counterpoint to that is, a field known as complexity, which really focuses in other sciences like chemistry and physics, where they try to understand complex systems, and they've tried to apply that to economics. And there's some interesting insights that I think can be gotten from that, where we can try to understand maybe what's really going on in the markets and maybe be able to make some important and thoughtful decisions. So first off, to understand that the economy really is a series of self-organizing interactions. And then one thing that it's really Ray Dalio said in one of his books is, well, the economy, if you really simplify it, it's one entity interacting with another, whether it's a person or a company, and just multiply that by 1,000,000,000,000, right? Well, unfortunately, all due respect, that's not what actually happens, right? It's not a linear relationship. It's not things adding up and then it just sums up to an economy, right? There are interactions, there are self-organizing markets, there are self-organizing entities, then there's competition, and then all sorts of things then change and modify, right? So we tried to then understand this, and economists use the term agents, and they sort of stole this from the physicists and the chemists. And here's the problem with that, right? So a quark, right? We know how it acts. I mean, there is a quark. It doesn't think, it doesn't change its mind. It does what it does according to certain laws. The same thing with polymers, right? They form, they interact, they create certain entities, but they don't change their mind, right? And that's very different, because now we're dealing with markets and we're dealing with human irrational behavior, or even if it's rational behavior, when new things emerge, things change, right? And so this creates several levels of complexity where when we try to model those things, it becomes very difficult. I mean, even modeling things like polymers and quarks and other things is fiendishly difficult. Now try to do that when those very entities can then change their mind. That's the problem when we try to use agents to define an economy, and that's really been the standard so far. So what's happening is, while there may be cooperation and competition, it changes, it modifies, it becomes irrational. That irrationality may turn into rationality. There may be other changes, other things. We have certain elements that create increasing returns, create competitive advantage where there's an adaptation, and even if that adaptation is not optimal, it still wins. And there's a couple of examples, right? VHS versus Betamax, right? Sort of like, well, Betamax was a better technology, but VHS had more of a distributed base, and so therefore stores just started carrying VHS only, and then the better technology didn't win. You could argue that that was somewhat irrational, right? And even the idea of using a QWERTY keyboard, right? This is always sort of cited, that the QWERTY keyboard for a typewriter was initially designed to actually slow the typist down, to make fewer mistakes and enable the mechanisms to work more freely. Well, we don't need that today, but we still have a QWERTY keyboard. So we've sort of stuck to this irrationality. That's very difficult to model. And then human behavior in and of itself, it's based on a fear and anticipation. It's based on a fear of loss being more valued than the idea of gain, right? So we understand that, and that's the work of Simon Seversky and Daniel Kahneman. We've sort of seen all of this in place. Now try to model that, and we have, what I'm defining as, we have the third order effects. And this is really coming from mathematics, right? So in mathematics, we talk about the second order effect, the differential equations, where you have things are changing. Then the second order differential equation is they're changing at a changing rate, right? And so while the second order may be negative, that means it's still increasing, but increasing at a decreasing rate. Think about, you're in your car, you're still going forward, but you're slowing down, right? So your second order differential equation is now negative, right? Well, we try to model that, but the problem is that there are really three definitions of kind of time to be modeled, right? The first is the present. We see what happens, we see where we are, and we make decisions based on that. But then we also make decisions based on an anticipated future, right? So we say, well, we think we'll be making more money in the future, so we'll spend some money today. Or there's a fear of a recession, so maybe we should hold off on our spending. Or maybe there are bargains to be had given that recession, maybe we should increase our spending, right? So we have the present, but then we also make decisions based on an anticipated future, but then that future can change, right? So then you have that realization of what's happening, and you make decisions and choices based on that. And so this is where we get to complexity, right? We really can't model that out. And again, let's go back to the automobile as an example. You're in your car, you see traffic slowing, you slow down, you anticipate that you'll have to come to a stop, but then what you're seeing clears up, so then you accelerate, but then there's another delay up ahead. You know, those of us who've driven in California understand this concept completely. But you're really, changing at a decreasing and an increasing rate, and you're anticipating what's going to happen, and that changes your actions, but then new information is made available, then you change your actions based on that, right? Now imagine that in an economy. Now try and manage that and model that with people cooperating, people competing, people, creating new entities, other entities getting out of the way. This is what happens, and this is why what we do is we realize what's happening, we refine our actions, but then we keep repeating that process. And so that becomes this spiraling impact that's, I'd say it's difficult to think about managing it and modeling it mathematically. I would say it's impossible. The mathematics can look very interesting and complex, but you still can't get this nuance, and you are certainly not able to predict this kind of behavior, right? So the world is at non-equilibrium. And that's really the point. The mathematical models that we see in economics assumes ultimately we get to some kind of equilibrium. We really don't. I mean, I know there's that belief, well, supply and demand, right? So you get a price, and that's supply and demand. That's a very simplistic model because there's not one company offering one product with one bit of supply. Supply changes, there's supply chain disruptions, there's manufacturing disruptions, there's innovation, there's different cost and pricing, and all things are very dynamic. There's no truly kind of settled price in any one given time that you can truly predict, and that's really the point here, right? So you have acceleration that decelerates, you have deceleration and acceleration that accelerate and decelerate, and all that becomes, fiendishly difficult to try to understand. So the fundamental point here is no economy is ever in equilibrium. No market is ever really in equilibrium. You really can't predict what that equilibrium would be. And that's really the point. So equilibrium, the way I'm defining it, is you predict where a market's going to be, where it's going to settle, where a price will settle, where a growth rate will settle, where a competitive dynamic will settle. It doesn't settle to the point where it can be predicted. It ultimately does reach a point where you have a price, you have competition, you have those things, but you can't predict them. And it's equilibrium that we're looking for to enable us to predict. Right? So that's not what happens. What happens is complexity. And again, we're stealing this from the scientific world, but there's constant creation, there's constant cooperation, but there's competition, right? So all economies, small, large, global, they all self-organize, and they self-organize around markets. Those markets change. They self-organize around competition. That competition changes. It changes because there's innovation, there's disruption, very famously creative destruction, right? Well, things are destroyed, things are created. That's the world that we live in, and that's the market that we live in. And so challenging and predicting that is also very, very difficult. But what we understand is we have these levels of complexity, and trying to understand the dynamic nature of how things change. But the real point here is we can understand that things are changing at increasing rates, either good or bad. And when things start to change, they become nonlinear. And this is really the point to complexity, that there are nonlinear relationships. If I buy something at a store and somebody else buys something else at a store, those are considered separate transactions, but they add up to an economy. So they ultimately add together. Then they motivate other people to do other things, maybe create other products, create other services, and things become nonlinear very quickly. And that's really the point. And we've seen this in recent examples with technology companies, as we've pointed out previously. Well, there's only one search engine, Google, right? Who uses the second best search engine? Well, Bing may have a point about that. And that's a really interesting example now. So everyone uses basically Google. because it's the best search engine. So Google has a nonlinear relationship to that market. Now Bing is coming along with Microsoft, and Microsoft has now chat-GBT relationship, so they may leapfrog with new technology. And so you have something very complex, but it will be nonlinear, right? So in the sense that if chat-GBT is incorporated into Bing, and that's a better search engine, then suddenly that will be at an increasing rate. Well, now Google needs to respond, right? So you have these nonlinear relationships causing creation, causing destruction. And that's really what's happening in the market. And the way to predict that is to, one, assume there'll never be an equilibrium. It's not as if Bing will settle one place and Google will settle another place, and that's the way things are. That's the way things are now. But now we have this creative destruction with this AI tool that will definitely change the dynamic. And whatever change, that change will happen at a nonlinear rate in an increasing or decreasing rate. And that's the interesting thing. And that's the thing to point out when making decisions in markets, to know that it will be a nonlinear relationship, to know that there'll be some form of acceleration or deceleration. Traditional mathematical models that try to predict that, I think, are useless because they're so inaccurate. We ignore that. But what we can do is look at relationships as they are and as they are changing, and then assume that creation or deceleration of value. Again, when markets change, we've seen this, and Nassim Taleb in The Black Swan has talked about this often, where he said, well, things change slowly then very quickly, right? That's a John Maynard Keynes quote. But basically, relationships are convex or concave. In other words, they're nonlinear. They're nonlinear positive, nonlinear negative. And understanding those relationships is how we make more effective investment decisions, more effective economic decisions. And they're very challenging to be modeled. And that's really my point, that you have these self-organizing interactions that define an economy, but it's never stable and it never gets to a point of equilibrium. It's always changing, right? So you have these third order effects. You have the present, you have anticipation in the future, then you have events unfolding that change that anticipation, right? So you have those three levels of effect. And it's always going to be a non-equilibrium circumstance, right? So things will change, changing at an increasing rate, either positive or negative. And that's complexity. And that's really my point. So the model that we use is the world is complex, and we try to take advantage of these nonlinear relationships because things will move in a convex or concave manner, and understanding that is the basis of this presentation, where we understand that is the world is complex, the world is nonlinear, we have these non-equilibrium circumstances, and this is the way the world competes and how economies really change.